कैमरा कहाँ गया ये लोग, फिर ढूंढ के लाओ। किधर क्या आवाज है?
So, what is your Yeah, a theory that defines the universe.
Physics has existed and evolved with humanity. It had been there in the observation that wooden logs are easier to roll than to drag, and has been in the observations of the Hadron Collider. However, the present form of physics, as a science of observations and theories, and then inventions based upon the predictions of those theories, has come up with the Industrial Revolution. Physics has changed since then, from building of levers to lift things and pulleys, into cameras recording videos like this one, into computers processing massive amounts of data, and even allowing voiceover of this audio to the animation which were not even created at the same place or time. The scope of physics and its complexities have grown. It is now not just concerned in making simple observations and solving everyday problems, but rather making theories to solve the ideas proposed by the older theories. We are now asking deeper questions about our existence, about the universe and its formation and its working. And we have a theory with beautiful logic and explanations backed up by strong mathematical equations called the string theory. However, the string theory is not our first approach to a holistic definition of the universe. In fact, the theory makes much more sense when backed up on the Standard Model. The Standard Model is a theory that defines the universe as a framework of fundamental particles, not just the simple subatomic protons, neutrons, and electrons. The fundamental particles are divided broadly into two: the fermions, or the particles that make up matter, and the bosons. The fermions are of two kinds: the quarks and the leptons. The quarks exist in pairs of three: the up and down quark, the charm and strange quarks, and the top and bottom quarks. The up and down quarks make up the nucleons, while the others are produced only in high energy interactions of the Hadron Collider. However, being more massive, these higher quarks usually decay into the former ones. The leptons include the electron, the muon, and the tau, and the associated electron neutrino, muon neutrino, and the tau neutrino. The electron makes our atoms, while the other leptons are produced only in high-energy particle accelerators. The other kind of fundamental particles are bosons, the particles that are force carriers of the universe. Fermions interact with one another by the means of bosons. The quarks are held up together into nucleons by the strong force due to gluon. Electromagnetic force is carried between matter by the photons. The W and the Z bosons are involved in the fermion decays and the nuclear interactions. The recently discovered Higgs boson is a particle that associates mass to other particles that interact with it.
Now, in the Standard Model, we've talked about matter being formed. We have quarks and we have leptons and all those subatomic particles, sub-electronic particles forming together, and we have electrons and everything. And we even talked about how forces are propagating. We have bosons that are carrier of forces, like we have the matter interaction, the electromagnetic forces being carried by the particle called photon. So in general perception, we have almost everything in the old model. But a very profound thing yet remains in that model, and that is we have a very fundamental and very large scale force called the force of gravity. Now, when we come to include gravity into the perspective, when we start to use a particle based theory for gravity, we would have something called a graviton. So, everything seems very fine. But when we try to include graviton into a perspective, when we try to perform mathematical functions on graviton and their interactions, we see something peculiar. We see that those interactions give out energies that are seemingly infinite, and such possibilities cannot be happening in a very natural, very fundamental and balanced universe. So we see that the Standard Model, although seems very sophisticated, very quantum mechanical, has an intrinsic failure of not having gravity to itself. So now our work starts, or everything begins with thinking about what should we do to solve this problem? What should we bring in our perception that this problem of gravity not being included as a fundamental thing in the standard model can be solved?
The graviton problem comes with the standard model of atom. But long before, in 1915, Einstein had proposed his theory of general relativity. This theory explains about universe as a fabric of space and time itself. Whenever mass of matter is added to the empty universe, it causes bending or curvature of this fabric, thus propagating the force of gravity.
Sir Isaac Newton explained the force of gravity with his universal law of gravitation. However, the law could only explain properties and characteristics of the force as observed before. It failed to explain the origins or causes of the force and how it could affect beyond medium in the universe. It was only with the general theory of relativity given by Albert Einstein that the force could truly be explained. The theory considered universe as a construction of the dimensions of space and time. The fabric of space and time extended through the universe, and matter could bend this fabric, causing curvatures. It was through these curvatures that the force of gravity was created and also propagated in space and time. Thus, the curvatures in space and time itself carried the force of gravity and allowed matter to realize about other matter, mass to understand that there's more mass in the universe.
So with general relativity, we found that the medium that transmits gravity is the curvature of space-time itself. Now a German mathematician came to the scene and tried to relate this curvature of space-time with electromagnetic force in a universe with 4 spatial dimensions to be precise. Now when he did the calculations, he found that same equation that Maxwell had once used to describe the electromagnetic force. So he concluded that maybe to define some other force, we might need additional dimensions.
If we have those extra dimensions, where are they? Why do we not feel their impact in our real lives? That is the question.
We live in a three-dimensional world. We have quantum theory for the small atoms and Einstein's theory of space-time relativity. But these theories do not fit together until we go into hyperspace, space of more than the 3 dimensions as we know it today. It was evident that adding extra dimensions could potentially help us unite the laws of physics. Now, for these additional dimensions to exist, there could be 2 possibilities. They might be big enough for us to see them and feel their impact, or they might be tiny, curled up, or compactified to a single point. Scientists believe that if those extra dimensions do exist, which are really small, because if they were bigger, we might have felt their impact somehow in our lives. But since we don't, we have a feeling that they're really small, so tiny that there would be no way for us to detect them. Scientists believe that an extra curled up dimension would have a radius as small as the Planck length, which is the tiniest scale they can make sense of. And maybe that is the reason we do not feel their impact.
If particles like photons and gravitons look like the way we imagine a particle, then all the forces and interactions that would happen with it would all come to a single point. But since our 3-dimensional points are no longer points but tiny curled up dimensions, then how are those particles spread in those tiny dimensions? How do they exist in those dimensions? Now this basic question leads us to string theory.
Now that the points are no longer dimensionless, particles are not just solid balls restricted to a point. They have geometry within. They are vibrating filaments of energy spread across in these ultra-tiny dimensions, named as the strings.
So the point particles of the standard model are no longer particles. They are actually vibrating filaments of energy which are packed up into very tiny dimensions that are curled within a point. So the old point dynamics does not make sense here. So the question comes, how do those strings move about space and interact with each other?
Just as a point moves about in space, tracing a trajectory at a time, a string covers a surface. To describe the evolution of strings in a possibly theoretic way, as in quantum physics, we will consider all possible geometries that the string can trace over time. It can follow a specific trajectory at a time, vibrate in a certain way, and also duplicate itself, affecting to the emission of a particle, and also reunite itself, affecting to reabsorption of the particle. Now, looking up at all the possible geometries that a string could form, string theory automatically includes interactions. Speaking of which, the interactions according to the standard model occurred all of a sudden, which brought infinities while including the graviton in the model. But in string theory, particles are emitted cautiously, step by step, which also allows us to calculate how the gravitons interact with other particles, thus describing gravity at the quantum scale.
But this theory falls short for two major reasons. Firstly, this theory predicted the existence of bosons only and not fermions, which means that photons could exist but not quarks or leptons. This seems kind of absurd because in the universe there's not just interaction taking place, but also matter that exists. Secondly, this theory predicted the existence of a particle with an imaginary mass called the tachyon. The existence of such a particle is an indication that the model is unstable.
The addition of spinors not only confirms the existence of fermions but also removes the tachyon from the model. The older string theory required a universe with 26 dimensions, which made it really difficult to describe our universe. But according to superstring theory, with the introduction of supersymmetry, it only requires 10 dimensions.
After the addition of spinors, the theory exhibited a symmetry between fermions and bosons. It predicted the existence of as many bosons as there are fermions. This is called supersymmetry.
So this is the string theory. The particles are made up of tiny vibrating filaments of energy known as strings, which constitute the matter around us and also propagate the forces in nature. So in a way, this theory defines everything around us, and therefore it was named the theory of everything.
Well, yes, there are strings that vibrate in multitude of patterns. Each pattern corresponds to a different particle. And there are different sets of particles governed by different laws of physics. Also, there are dimensions that are arranged in about 10 raised to 500 ways, and only one out of them corresponds to our universe.
So what about the others?
Well, that is the thing. Maybe those other arrangements correspond to different universes. Maybe there are so many universes that you've not even imagined. And this is why string theory leads to a very peculiar and interesting idea of multiverse.
Certain men in Russia long ago. He was big and strong in his eyes.
देखो इन्हें ये है ओस की बूंद
Maybe humanity is not just the thing that it is. Maybe there's not just one universe. Maybe what we ever thought in science fictions was actually reality. What if there were so many universes that you could not even imagine, like billions, trillions, zillions of universes? Just think about that.
नहीं तो बोल गया तो
It's the motherfucking Eagle Double G. Snoop Dogg.